Hi everyone. In this video, we will begin our second run through the material for this course, this time slowing down to carefully consider basic definitions and prove each of the theorems that we looked at in the first run through as we strive to understand more completely the fundamental structure of the theorems that make up most of a basic Calculus 1 or 2 course. So to begin, we want to start by considering sort of the basic topology and structure of the real number system. Over the course of the next two videos, we're going to work to address the following questions, which will be fundamental to our further study. In particular, we want to understand what the structures are that are needed on a given set in order to first do basic arithmetic. Second, to compare distances between things in order to define some notion of closeness. And finally, to calculate limits. We'll see that we need varying levels of structure in order to do each of these things. And by the end of this video, we will have started to answer the question of what the exact structure is that's needed to do all three of these things simultaneously. To begin, we want to start with the definition of a field. So a field is a set together with two operations, which we're going to call addition and multiplication, that satisfy the following axioms. Now, this might look sort of intimidating at first, but let's sort of take these carefully one by one, and we'll see that actually they're not quite so quite maybe as scary as they seem. So 1A and 1M both say that the set is closed under each respective operation. So 1A is the set is closed under addition. 1M is the set is closed under multiplication. That simply means that if I take two elements of my set and add them together, I get another element of my set. And if I take two elements of my set and I multiply them, then that resulting element is also in my set. 2A and 2M say that each of our operations are associative. So addition is associative and multiplication is associative. That simply means if we have three things, for example, that are added together, it does not matter whether we add the first two and then add the third, or whether we add the second two and then add in the first. So if we were to write this more formally, right, we might say quantity A plus B plus C is equal to A plus quantity B plus C. Same thing works for multiplication. The third properties, 3A and 3M, say that each of the respective operations is commutative. So A plus B is equal to B plus A, and A times B is equal to B times A. 4A and 4M both give the existence of additive and multiplicative identities, respectively. So 4A says there is an additive identity. An additive identity is a element of your set of your field F, or sorry, of your set F, so that when you add any number to that, you get that same number back. So often if we're thinking about the real numbers in addition, that additive identity is 0, right? A plus 0 is equal to 0 plus A is equal to A. 4M gives you the existence of a multiplicative identity. So that operates similar to the additive identity except for multiplication. Typically, we think of this when we're thinking about the real numbers, and multiplication, we're thinking about the number 1. And so A times 1 is equal to 1 times A is equal to A. 5A and 5M both give you the existence of additive inverses. So 5A says every number has an additive inverse, and maybe sort of adding on here in F, right? So in your set. So for real numbers, these are just the negatives, right? So 5 is a real number. Negative 5 is also a real number. 5 plus negative 5 is 0, which is why 5 and negative 5 are additive inverses. Likewise, negative 10's additive inverse is 10, because negative 10 plus 10 is 0. And then 5M, there's a small stipulation here. Every non-zero number has a multiplicative inverse. So here, right, if I have the number 2, I also need 1/2 to be in my set, because 2 times 1/2 gives me 1. Zero obviously does not have a multiplicative inverse, so we don't need to worry about that. Now, notice if we look at 1a through 5a and 1m through 5m, each of these sort of lists, this deals with properties of sort of how the set acts with respect to addition. This list deals with how the set behaves with respect to multiplication. Number 6 deals with how multiplication and addition interact with one another. So this says multiplication distributes over addition. So A times quantity B plus C is equal to A times B plus A times C, the typical distributive property. That really tells you something not just about multiplication and not just about addition, but about how multiplication and addition interact with one another. Now, just a few brief comments about each of these. If you look at 1a plus 1m, if you actually look at some other definitions of a field, you won't see 1a and 1m. You'll actually see that they just up here will say a field F is a set together with two binary operations plus and times. Being a binary operation necessarily means you are closed under each of those operations. So these first two basically just say plus and times are binary operations. These second two, these are really don't have so much to do with the set, although occasionally the actual set comes into play. These are often just inherited properties of the operation. So even if we restrict ourselves to some subset of the real numbers, for example, and use standard addition and multiplication, you're going to sort of inherit these for free. So often, but not always, you almost get these for free just from the definitions of the operations. Um, and as I said down here, the really special thing here is this says something about how addition and times and multiplication interact in this specific way. These existence of inverses here in the middle, again, they're just making sure you include all the inverses in your set, the appropriate inverses in your set. But again, the sort of important part here is that they exist in your set that you're looking at. So perhaps it's most helpful first to start thinking about some sets and operations that we know and considering whether those sets with given operations are a field or not. So I have listed here 5 different sets, and I want to consider each of those sets with the usual addition and multiplication. So we're not doing any unusual operations here. These are just standard addition and multiplication. And the question I want to answer for each of these is if I take these with the standard addition and multiplication, do these sets with those operations form a field? What I would encourage you to do is pause the video here and go through each of these for yourself. So for each one, start with the real numbers. Does the real numbers with standard multiplication and addition satisfy all 11 of those axioms that you saw on the previous screen? Then do the same thing with Q. So as a reminder of some of these sets here, Q is just the rational numbers, right? So this is just all the numbers of the form P over Q, where P over Q are integers. And of course, I don't want that denominator to be 0. So these are all the fractions, all the numbers that can be expressed as ratios of two integers. This set down here, so you see the real numbers and the rational numbers, this sign in between is delete. So these are all the things that are real numbers but are not rational numbers. We might also refer to these as the irrational numbers, right? So here, these are just the irrationals. Down here we just have the integers, right? So we might often just express those in sort of this form, right? And we just refer to these as the integers. And then finally, we have here the set of complex numbers. So we could express this as the set of all numbers of the form a plus bi, where I here is the imaginary unit, right? So this is the number whose square is -1. And these are just all the numbers of the form a plus bi, where a and b are just any old real number here. Okay. So I invite you to sort of pause the video, take a second, and go through each of these. See if you can determine whether each of these forms a field with the given operations or not. Okay, so going through these, it's probably no surprise that the real numbers do form a field with the usual addition and multiplication. So thinking back through those properties, if you add two real numbers, you get another real number. That's 1a. If you multiply two real numbers, you get another real number. That's 1m. Great. Addition and multiplication are both associative. That's 2a and 2m. Check. 3a and 3m are about commutativity of addition and multiplication. We know that regular addition and multiplication are commutative. So great, that also works. 3a and 3m, check. 4a and 4m are about the existence of additive and multiplicative identities. 0 is a real number, 1 is a real number, check. 5a and 5m are about inverses. So the additive inverse of a real number is also a real number, right? So if you take any real number a, negative a is also a real number, and a plus negative a is 0. So every number has an additive identity that's also a real number. Every non-zero real number a has a multiplicative inverse 1 over a, which is always defined as long as a is not 0, so that a times 1 over a is equal to 1. And then finally, 6, addition and multiplication. The standard addition and multiplication satisfy a distributive property. So all of the conditions of a field are satisfied. So the real numbers are a field. Great. Now, what about the rational numbers? Well, you might start to see that a lot of these things you'll sort of get for free. So if you think about 2a, 2m, 3a, 3m, and 6, those are really properties of the operations multiplication and addition. It's always associative, it's always commutative, and it always satisfies a distributive property. At least, right, for any subset of the real numbers, and at least all of these are subsets of the real numbers. So those we're sort of going to get for free. The ones that we really need to focus on are the closure, the identities, and inverses, right? Those are the ones we really need to make sure are satisfied. So for closure, is the sum of two rational numbers always a rational number? The answer is yes. If I add, 1/2 and 1/3, right, that's going to give me another rational number, right? If I just add it out, that would give me 5/6, which is also a rational number. And in general, right, you could show that if you add P over Q plus R over S, right, you're going to get, I'm not going to do this for every example, but let's just quickly run through this. So this would be PS over QS plus QR over QS, which would be equal to PS plus QR over QS. If I'm assuming that each of these is a rational number, right, that means that P, Q, R, and S are all integers. The product of two integers is an integer, and then the sum of two integers is an integer. So the numerator is an integer, the denominator is an integer. Since P and Q are both not 0, then since Q and S are both not 0, then Q times S is also not 0. So this is also a rational number because it is a ratio of two integers. Okay. We can do the same thing for multiplication. In fact, it's a little bit easier for multiplication because it's easier to multiply fractions. So you get closure of Q under addition and multiplication. Inverses, okay, so additive inverses will be good. If I have P over Q, its additive inverse is just going to be minus P over Q. Q was an integer, so Q is an integer. P was an integer, so minus P is also an integer. So great, we have the existence of additive inverses. Those will add together to be 0. Multiplicative inverses, right? Assume I start here with a non-zero number. That means P is not 0. Then Q over P will be well defined and will also be a rational number. And so we have the existence of multiplicative inverses. So it'll be PQ over PQ, which is 1. Okay. I actually did these a little out of order. Sorry. So this is the existence of the inverses. I also need the existence of the identities here and here. This is easy because I can write this as 0 over 1. So it's definitely a rational number. I can write this as 1 over 1 or 4 over 4. It's also a rational number. It can be expressed as a ratio of integers. So my identities, my additive and multiplicative identities, are both also rational numbers. So even though I've done these slightly out of order, right, I have established that the rational numbers satisfy all the properties, and so these also form a field. Okay. Now, what about the irrational numbers? So the actually first thing we'd want to check, right? So again, we're going to sort of skip over the associativity, the commutativity, and the distributive properties because those are all going to be satisfied. Let's start with closure under addition. Is it true that if you add two irrational numbers together, you always get an irrational number? Well, take your favorite irrational number. There's mine. Okay. But this could equally work with square root of 2, which is irrational. It could work with e, which is irrational. Pick any irrational number you want, as a matter of fact. Well, if the irrational numbers formed a field, then minus pi would also have to be irrational. In fact, minus pi is irrational. And minus square root of 2 is irrational. And minus e is irrational. Okay. And if I add two irrational numbers together, if I want it to be closed, I should get an irrational number, but 0 is not irrational. So the irrational numbers fail the closure properties, both under addition and multiplication, as a matter of fact. So they fail 1a and 1m. They do not form a field. Now you could go through the rest again. Associativity and commutativity would hold. You would fail the existence of inverses because, again, 0 and 1, your additive and multiplicative identities, are not irrational numbers. So you would fail that. The existence of inverses would be okay. The additive inverse and the multiplicative inverse of an irrational number is also irrational. And then distributive would be okay. But you would fail 1a, 1m, 4a, and 4m if in terms of going through those properties. Of course, it's enough to show that you fail one to show that it's not a field. So if you're ever, working on a problem and you're asked to show it's not a field, you just need to show one of them fails. You don't have to show that any more fail. All right. The integers here, z, these actually, if you start to go down the list, they'll be okay for a while. So they're closed under addition and multiplication. You get associativity, you get commutativity, you get the existence of additive and multiplicative inverses. 0 and 1 are both integers. You get additive identities, so you get 5a, but you fail 5m. You do not have multiplicative inverses. So, for example, if you want to take and add, if you take the number 7, right, and you want to find its multiplicative inverse, well, that should be 1/7, but that is not in my set Z. So this is not a field. This only fails 5m. Now, finally, the complex numbers, we won't be dealing with these a lot in this course. We're primarily focused on functions from R to R, but it's nice to think about other examples from time to time. These, in fact, do form a field. Okay. So you get closure. So the sum of two complex numbers is a complex number. The product of two complex numbers is a complex number. Addition and multiplication are associative and commutative. You get 0 and 1. The additive and multiplicative identities are both complex numbers. They're of the form 0 plus 0i and 1 plus 0i, respectively. And you get what's a little harder, right? Additive inverses are not hard. Multiplicative inverses, you have to think a little bit, but there are multiplicative inverses. And then you get a distributive property as well. So again, the complex numbers do in fact form a field. And so that's just one more example of a field, maybe something that's a little beyond just some of these other examples that are either R or subsets of the real numbers. All right, great. So what we see here is there are some sets that are fields, there are some that aren't. And being a field essentially gives us the basic structure we need to do arithmetic. So back to that first question, right? If I want to sort of do things in calculus, I need to be able to do basic arithmetic. And a field is sort of the minimal structure in order to be able to do that arithmetic. Now, there are some other things that follow from those field axioms. Okay, so for example, there are cancellation laws that you'll notice these didn't appear anywhere in our field axioms, but they do follow from those field axioms. So if I have x, y, and z real numbers, or in general, if they're just elements of a field, then if x plus y is equal to x plus z, then y must be equal to z, right? So it's a cancellation law because I could cancel an x over here and cancel an x over here. If x times y is equal to x times z and x is not equal to 0, then y is equal to z. I'm not going to write out a full proof here, but just to give you the idea, right? If you have that x plus y is equal to x plus z, I can add the same thing to both sides. I'll add a negative x to both of these quantities. Okay. Now, by the field axioms, it's associative. So this is equal to I can do this. Now, negative x by definition is the additive inverse of x. So that gives me 0 plus y is equal to 0 plus z. 0 is the additive identity. So I get this. Now, notice I mean, this is like the most basic cancellation. You've been doing this your whole life. But notice that even in order to be able to do that kind of algebraic manipulation, you needed to use a number of the field axioms. So this first part gives you the existence. So you're using here the existence of an additive inverse in order to be able to add this. So you're using additive inverses here. From here to here, you're using the associativity of addition. From here to here, you're using, again, you're using here the definition of the additive inverse, right? And from here to here, you're using the definition of the additive identity. So here, even in this to prove this very basic sort of fact about cancellation, you need at least 3 distinct field axioms in order to be able to justify that. A proof for multiplication works in a very similar manner. You're just using multiplicative properties. So again, this field sort of gives you just enough structure to start doing the kinds of algebraic manipulation that we're going to need to do if we want to prove the theorems of calculus. Now, all of that gives us structure to do arithmetic. Now we also want enough structure to be able to compare things, to talk about closeness or to talk about relative sizes of things. So we're going to start by defining what it means for a set to be ordered. So we say that a set U is ordered when it has some relation, we're going to use the very inventive notation less than, such that the following are satisfied. So the first thing I want satisfied is for each x and y in my set U, so for 2 arbitrary elements in my set, I want to know that exactly one of the following is true. X is less than y is less than x, or x is equal to y. Okay, so either x is less than y, y is less than x, or x and y are equal. And exactly one of those should be true. The second thing I want to be true is that I want for any x, y, and z in my set, I want that if x is less than y and y is less than z, then x is less than z. So this first property is often called like a comparability property, right? You want any two elements to be comparable to one another. So if you take two things, you should be able to say that either one of them is less than the other or they're equal to each other. And only one of those should be true. The second property is often called a transitivity property. So you say if I have x is less than y and y is less than z, then I should be able to say that x is less than z. Okay. Now, for the real numbers and standard less than, a standard meaning of less than, right? We can pretty quickly see that that's going to be an ordered set. So if we take the real numbers with the usual less than, right? We get these for free. Okay. What's interesting then is to start thinking about other things here, right? So you might again want to pause for a moment, consider these are the same sets we talked about whether or not they are a field. For the first four, I could ask the question, are these sets ordered with the usual less than relation? So that's the first question we can ask. Here, if I talk about the complex numbers, less than doesn't make sense in the standard way. So the question here might be, is there any sort of way we could order this set of complex numbers? So take a moment, pause the video, think about these questions, and then unpause in a minute, and we'll talk about this a little bit further. So again, we've already talked about the real numbers with the usual less than relationship. Certainly, if I take any two real numbers, either they're equal to each other or one of them is bigger than the other, right? So that first comparability property works. The second property, if x is less than y and y is less than z, then x will be less than z. Great. Now, the next three, you can make exactly the same arguments. All of this still works. So sort of an interesting thing to note here, because of the definition of ordered, as soon as a set is ordered, all of its subsets are also ordered with that same relationship, right? Because it works for any x and y and r, it also works if you just take x's and y's in the rational numbers, or x's and y's in the irrational numbers, or x's and y's in the integers. So all of these sets are in fact ordered sets. So the first thing I want to sort of point out is that being an ordered set is different from being a field, right? You can be one and not be the other, right? So you can be a field and not be an ordered set. You can be an ordered set and not be a field. So the irrational numbers do not form a field, but they are an ordered set with this order relationship here. The integers, not a field, but can still be considered an ordered set with this order relationship. So these are different things. These are different kinds of structures on a set. Now, for this last question, the complex numbers, you can in fact order these. And so it's worth just having, one more sort of example here. So I will say that the real number a plus bi is less than the real number c plus di if a is less than c, or, and to make this clear, I'm going to sort of put some parentheses here, or if a is equal to c and b is less than d. Okay, so the idea is I'm going to compare these two numbers by looking at the real parts. If the real part of this number is less than this, then I'll say, okay, this is less than this. If the real parts are equal, then I'll move to the complex parts and I'll say, okay, if this is less than this, then this complex number is less than this complex number. Now, it takes a little work to prove these properties. So the first thing you want to do is show that any two numbers are either one is less than the other or they're equal to each other. So take two complex numbers. Either one of the first part, one of the real parts is bigger than the other. Okay. And the real parts are just real numbers, right? So one of them is either greater than or equal to the other, or they're equal. Okay. If one of them is greater than or equal to the other, then you're immediately in this case and you can compare them. If the two real parts happen to be equal, then you move to the complex parts. Okay. The coefficient of the complex part is just another real number. So either one of them is less than or equal to the other, in which case you're in this case and you can compare them, or they're equal to each other. But if the real parts and the complex parts are both equal to each other, then your two complex numbers are equal, and so you have equality. So you can immediately show that in a fairly straightforward way, although you have to consider some cases, you can show that that first property is satisfied. The second property is a little harder because you have to tease out a number of cases, but the transitivity property does also work there as well. So we get this is actually this sort of strange definition of less than does actually form an order on the set of complex numbers. I will say, however, there's a lot of problems with this order. It's not particularly good for doing analysis. So we don't make use of it that often. But if you want to learn more about this, this is called lexicographic ordering. You can also use this to order vectors or order ordered pairs in the plane. So it's an interesting example of an order. Now, once we have an ordering, we can start talking about bounds, right? We can start bounding. So we can use inequalities now, right? Ordered sets essentially now allow us to use inequalities. So I can define this property of a set, which is called the least upper bound property. So let U be an ordered set. I'll say that U has the least upper bound property if anytime I take a non-empty subset of U that's bounded above, then that set has a least upper bound in U. So said another way, I'm saying that for any non-empty subset E of U, there exists some beta in U such that beta is greater than or equal to every element of my set E. So this first part is just saying beta is an upper bound. And the second part says if I have some other upper bound for E, because you can have many upper bounds, if I have some other upper bound for B or for E, call it beta prime, then beta prime necessarily is greater than or equal to beta. So beta really is the least of all the upper bounds, right? Any other upper bound has to be greater than or equal to it. If this beta exists, we call it the supremum of E, and we often just write this as beta is equal to the sup of E. Okay, so right, just taking an example right in the real numbers. So if you were to take the set of all real numbers from 1 up to 3, say not including 1 or not including 3, this set has a number of upper bounds, right? 4 is an upper bound, 17 is an upper bound, 100,000 is an upper bound. There are many upper bounds, but there is also a least upper bound, which is 3. So notice that 3 is greater than or equal to every element of this set, right? And also, if I look at any of these other upper bounds, they're all greater than or equal to 3. So 3 is the least upper bound. You can do this for sets that aren't just intervals. So you can also take, for example, all the numbers of the form 1 over n, where n is a natural number, right? So again, this is just sort of a collection of isolated points. But if I were to look at this, it has an upper bound, which is just 1, right? It also has a bunch of other upper bounds, 52, 17, anything bigger than 1 will work. But 1 is the least upper bound. So here, our beta would be like 1. Now, we are saying that a set U has the least upper bound property if every non-empty subset satisfies this condition. So we just, for example, looked at two subsets of the real numbers and showed that each of those has a least upper bound. But in order to prove that the set of real numbers has the least upper bound property, you'd have to do it for every non-empty set of the real numbers. Now, I'm going to tell you that the real numbers satisfy the least upper bound property. We are going to take that as a given. If we were in a course where we worked through a full axiomatic construction of the real numbers, then we could show that the real numbers thus constructed satisfy that least upper bound property. Often this sort of falls out of the way in which you construct the real numbers. You often start with the rational numbers, and then there are ways of building up the rest of the real numbers from the rational numbers. And in the way you do that, you can then prove that the real numbers satisfy a least upper bound property. The rational numbers, however, do not satisfy a least upper bound property. So you can take, for example, the following subset of the rational numbers. So take all the rational numbers such that when you square them, you get a number that's less than 2. So if you look at this, this is certainly a non-empty subset of the rational numbers, right? So there's the number 1 is in this set, for example, right? It's a rational number, and when you square it, you get a number that's less than 2. So it's a non-empty subset of the rational numbers. It does not have a least upper bound. Okay, so it certainly has an upper bound. For example, 4 is an upper bound for this set, right? 4 is not in this set, right? Because if I take 4 squared, I'll get 16, which is way bigger than 2, right? So 4 is an upper bound, 3 is an upper bound, 2 is an upper bound. But you can actually show, and in the book, actually, in one of the homework problems, they walk you through some steps for how you would actually show this. But the long and the short of it is essentially what you want the upper bound of this set to be is square root of 2, but square root of 2 is not a rational number. And notice that the condition here is that the upper bound of each set needs to be in U. In this case, it would need to be in the set of rational numbers. So the problem you have here is that the thing that sort of naturally should be the least upper bound is not actually in your set Q. And so that's what causes the issue here. Of course, if all you know, the only sets you have are the rational numbers, you can't just go, oh, it's square root of 2, because square root of 2 is not a rational number. So in actually proving this, you have to work a little more carefully to show that you cannot possibly have a least upper bound. But fundamentally, the idea is that the least upper bound should be square root of 2, but that's not a rational number. Now, notice that this is a definition. I'm now going to put up a theorem, right? So a definition is something we're just defining, and a theorem is something we are claiming is true. So we can look at whether or not a set has the least upper bound property. Now here's a theorem about greatest lower bounds. So if U is an ordered set which possesses the least upper bound property, and suppose I have a non-empty subset B, which is bounded below, then the greatest lower bound of B exists. We'll call that alpha, and that element is in your set U, and we call alpha the infimum of E and write alpha as infimum of E. So the idea here is as soon as your set has a least upper bound property, then not only do you have least upper bounds, you also have greatest lower bounds, right? So if I were to take, or to go back to this example 1, 3, a subset of the real numbers, it has a greatest lower bound, which is 1. If I were to again take this set 1 over, and this has a greatest lower bound, in this case, it's 0. Okay. So you also get sort of, as soon as you know you have least upper bounds, you also have greatest lower bounds. Now, you can actually prove this fairly quickly. So the idea is the following. And I'll just sort of give you the idea by looking at an example. Let's say you want to know something about the greatest lower bound of this. The idea is look at negative this set. So negate everything in this set. Okay. Now you get this. Since this was bounded below, this must be bounded above. Since this is bounded above and you're assuming that your set possesses the least upper bound property, then this has a least upper bound. That's -1. And then what you do is you show that if you negate this back, right, that this number you get by taking negative the least upper bound, you show that this thing is actually the greatest lower bound for this set. So once you have least upper bounds, you have greatest lower bounds precisely because you can translate it back to something about least upper bounds. You can again see the book for a fully worked out proof of that, but that's essentially what I've outlined there is the fundamental idea. All right. Now, immediately following out of this is a very important property called the Archimedean order property. So if we take two positive real numbers, call them epsilon and x, then there is some natural number n such that n times epsilon is equal to x. Now, to illustrate this, I think it's helpful to think about a number line. And we're starting at 0 here because both of our real numbers are positive. And this is sort of really interesting when epsilon is really small and x is really large. So imagine I take a really small epsilon and a really large x. What this property says is there's some natural number so that n times epsilon is equal to x. Thinking about this another way, I can sort of think about taking steps of size epsilon. So there's one step of size epsilon, 2 steps, 3 steps, 4, 5, 6, 7, 8. And what this theorem says is eventually there's some number of steps, no matter how small my steps are, there's some finite number of steps that will eventually lead me past x. So if I'm taking steps of positive size, I'll always get however far you want. I may have to take a lot of steps, but I will eventually get past that number. Now, the Archimedean order property follows from the least upper bound property. So to prove this, we are going to do what I think is now it's really sort of our first official proof, and it's going to be a proof by contradiction. Okay, so let's take a look at this proof. So we are going to assume to the contrary that for some epsilon and x, so I'm going to use this notation R plus, so I'm just meaning here they're positive real numbers. So for some positive real numbers, epsilon and x, the set of numbers of the form n times epsilon for all natural numbers n is bounded above. So right, if we assume this is false, which is what we're doing for a proof by contradiction. So if we assume this is false, that means we're going to flip the inequality, right? So n times epsilon is going to be less than x for every n. If this is false, then there is no n so that n times epsilon is greater than x. So it must be the case that for every natural number n times epsilon is less than x. So this set is bounded above by x. All right, well, that's great. I now have a non-empty set of real numbers, which is bounded above. I can apply the the least upper bound property. So by the least upper bound property, I can define beta to be the supremum of this set. All right. No problem. So what does that mean? That means that for any natural number, even the next natural number times epsilon must be less than x, right? If n is a natural number, then n plus 1 is a natural number. And for, sorry, uh, should be less than beta here. So n plus 1 times epsilon should be less than or equal to beta, right? Because beta is an upper bound for this set. This is some natural number times epsilon. This is an upper bound for this set. So beta should be greater than or equal to n plus 1 times epsilon for any natural number. Okay. Well, then let's see. What does that mean? If I rewrite this inequality, then that gives me sorry, n times epsilon plus epsilon is less than or equal to beta. And if I just subtract the epsilon over, that gives me n times epsilon is less than beta minus epsilon. Again, for any natural number n. But now, if I look at this, what does this say? This says any natural number times epsilon is always less than or equal to beta minus epsilon. Well, that means beta minus epsilon is an upper bound for this set. So this says then that beta minus epsilon, which, by the way, right, is strictly less than beta. This is an upper bound for this set. Okay. But that's a contradiction because we assumed here that beta was the supremum, which means we assumed beta was the least upper bound. But now I've shown that beta minus epsilon is also an upper bound, and beta minus epsilon is less than beta. So that's a contradiction. So hence, we have a contradiction. Since beta should be the least upper bound. And now, having arrived at a contradiction, we realize that our initial assumption was incorrect, and it must be that this is true, right? So the idea of a proof by contradiction is assume the negation of the thing you're actually trying to prove, show that that leads to some contradiction, then that means that the original statement must have been true, okay? We often end proof by contradiction with some sort of symbol. I sort of like this one where you have conflicting ideas here, right? So we have a contradiction, and so our original claim must hold. Now, the Archimedean order property, in this form, it's useful sometimes, but it actually turns out there are many equivalent forms of this, which are some of which I think are even more helpful than this particular form. So I will quickly close by looking at a couple of equivalent forms. So the following are equivalent. So each of these are equivalent to the Archimedean order property. So the first is that for any real number x, there is a natural number such that n is greater than x. So this essentially says that you can always find a natural number bigger than any real number. Said another way, this says the set of natural numbers is unbounded. You could never find an x that's bigger than all the natural numbers because there's always a natural number that's bigger than any x you might choose to be your upper bound. The second, the third one listed here. So for any positive real number x, there is a natural number n, so that 1 over n is less than x. Again, this is sort of interesting to think about when x is really small, right? What this is saying, this is sometimes called the squeezing in principle, because if you think about this, 1 over n No, we're saying no matter how small x is positive. 1 over n is always going to be positive. So what we're saying is no matter how small x is, you can always squeeze in a number of the form 1 over n between 0 and x, right? So you can make n bigger than x if you want, or you can make 1 over n smaller than any x. Okay. This last property, so for any positive real number x, there is a natural number n such that x is between n and n plus 1, right? This is just a nice way of sort of saying there's always some sort of last natural number before you cross over a real number x, and then there is some some natural number n plus 1, which is the first one below it. So sort of this partitions things out nicely, right? So these are all equivalent to the Archimedean order property, and these are all forms that we will explore more throughout the course. For one of your homework problems this week, I will likely ask you to prove that at least one of these is equivalent to the Archimedean order property as stated. We'll stop there for the day. Next time, we will look more in depth at really properties, other properties of sets. In particular, so far we've looked at properties that allow us to do arithmetic and to do comparisons of things. We still need to understand a little bit more about the structure we would need in order to talk about the limit. So what kinds of sets, what kinds of domains can our functions have so that it will still make sense to talk about the limit at some particular point in that domain? So next time we will work more through that, looking at definitions of metric spaces and open sets.